Good afternoon, everyone. My name is Ed Schlesinger. I'm the Benjamin T. Rome Dean of the Whiting School of Engineering, and welcome to our 2022 Billig-Croft Lecture. It's very exciting to welcome you all here to this event, as we have not hosted an in-person version of this lecture since the fall of 2018. So it's really an auspicious milestone that we're all here together in person, although one thing we learned in COVID is to live stream the event as well. Before I introduce the speaker today, I want to thank Gordon Croft for establishing this annual lecture in honor of his good friend, the late Dr. Frederick Bilig. Gordon, although he's not with us here, I hope he's on the live stream. I want to thank you. We are very fortunate to have you as a supporter, and I do hope that you will be able to join us on campus soon. Gordon graduated from Johns Hopkins in 1956 with a bachelor's degree in industrial engineering and has built a remarkable career in finance, including the establishment of the highly respected Croft Leominster Investment Management Company here in Baltimore, which he managed with his sons, Kent and Russell. Gordon has a true appreciation for the overall importance of engineering in our society. He thinks deeply about things that are important to our nation and is passionate about being a catalyst for change. He cares about the work being done here and stays involved with our programming and people on a regular basis. Gordon has been a most loyal supporter of the Whiting School in many ways, in addition to creating this lecture. He's provided scholarships for students from his home area of Port Tobacco in Charles County and established graduate fellowships and 3 faculty scholars. He also has provided generous, flexible support to the school to invest in interdisciplinary programs. In 2013, the university was thrilled to name Croft Hall in honor of Gordon's many years of commitment and generosity. So again, thank you, Gordon, for your foresight in establishing this lecture and for your overall dedication to the Whiting School. Gordon is always thinking about the most meaningful ways to give back to the school, and I know this lecture, in honor of his friend and mentor, Frederick Bilig, has a special place in his heart. So let me tell you a little bit about Frederick Bilig. Frederick Bilig received his undergraduate degree from Johns Hopkins in mechanical engineering in 1955. After Hopkins, he began his stellar career at the Applied Physics Laboratory. Sharing the accomplishments of Dr. Bilig would truly take all our time today. I hesitate to even summarize the depth and breadth of his professional achievements and contributions. He was a true pioneer and a giant in his field. During his remarkable career at the Applied Physics Lab, Dr. Bilig focused his research in the area of high-speed, air-breathing propulsion for advanced flight vehicles, including pioneering work for the Air Force in external burning and supersonic combustion. In 1996, he retired as associate head and chief scientist of the aeronautics department at APL. He also had a remarkable generosity of spirit and mentored many. In the spirit of generosity that Frederick Bilig embodied, Gordon Croft created this lecture to bring inspirational people to our campus with the hopes of motivating our students, faculty, and alumni, and all members of the Hopkins engineering community. I also want to thank Frederick Bilig's daughter, Linda Baumler, and her family for joining us virtually today, and I hope to welcome you back to campus at a future iteration of the lecture. And now, I'd like to introduce our 2022 Billig-Croft lecturer, Ken Hibbard. Ken Hibbard received his BS in Aerospace Engineering from the Pennsylvania State University and his MS in Systems Engineering from the Johns Hopkins University. He's worked at the Johns Hopkins Applied Physics Laboratory for 20 years and at NASA Goddard Space Flight Center for 7 years prior, specializing in project systems, engineering, and the design, development, and implementation of robotic space missions. He has served on numerous NASA missions, including ACE, SOHO, SWIFT, Messenger, and New Horizons, and has led the development of various proposals and concepts, including Europa Clipper, the Titan Mare Explorer, and the EO Volcano Observer. Today, he is the principal professional staff and the mission project systems engineer for the Dragonfly New Frontiers mission to Titan. I have to stop for a moment and say, for me, just the name alone as well as what this project is all about, is one of the coolest things that I think is going on at the Applied Physics Lab. And we're so fortunate to have Ken here to join us and to speak about it. Ken?
Thank you. Good afternoon, everyone. I have to admit, I'm humbled and honored to have the opportunity to speak with you all today. And I'm eager to share with you some information about Dragonfly, NASA's latest New Frontiers mission that is intended to go study Titan, the largest moon of Saturn. Additionally, I hope that providing some insight into my career path and kind of what led me here may be beneficial, particularly for some of the students or younger people in the audience, to help understand all the possibilities that the world has to offer when you get out into it. So with that, I think the intro already gave a little bit about my background. So indeed, I got my BS in aerospace from Penn State, and as highlighted here, my MS in systems engineering from Johns Hopkins. I started my career at NASA Goddard, where I spent the first 7.5 years or so primarily focused on heliophysics and astrophysics missions. Afterwards, I moved over to Johns Hopkins Applied Physics Laboratory, or APL, and I came over there primarily because I wanted to get involved in planetary science. And so there I've had the opportunity to work on some exciting programs like Messenger and New Horizons, but also on a number of proposals and new concepts. I've also been fortunate that over the years, I've been trusted with various leadership roles, leadership within my projects, but also entrusted as a supervisor and a line manager within the organization at APL. And if you know anything about APL, they're incredibly talented people who don't always like to be managed. And so that sometimes is a feat in and of itself. So the first major project that I worked on was called SOHO. It was the Solar and Heliophysics Observatory. It was an ESA-led mission where NASA was under contract to launch and perform post-launch operations. SOHO was a big budget mission at the time. It was about $1.3 billion back in 1994. And so, just inflate that to today. And it's a fairly high budget mission. I began my career doing mission operations. NASA likes to categorize the life cycle of a mission into different phases, A through F. Phase E is the operational phase, and it's really what starts at launch, but it's also when you achieve the purpose of the mission, right? No one really pays us to build these spacecraft and launch them because it's fun. It is, but we don't get paid to do just that part. They ultimately want you to achieve something. You have to make a strategic measurement. You have to accomplish certain science. You want to expand our knowledge. In SOHO's case, its intended purpose was to study the sun and the sun's interactions back with the Earth. And so in order to do that, it had a bit of a unique orbit. We orbit the Earth's L1 Lagrange point. And so we're on a point on the sun-Earth line where the gravitational pull on the spacecraft by both the Earth and the sun are roughly equal. So it lives about 1 million miles from Earth and about 100 million miles from the sun. But that position also gave it an uninterrupted view of the sun and the ability to nearly continuously relay that information back to Earth. A wise person once told me that you will learn far more in your failures than you ever do in all of your successes. That was never more true than on SOHO. In 1998, a little more than 2 years into the operational mission, we suffered what we've termed the mission interruption. During a series of maneuvers, we actually lost control of the spacecraft and it started tumbling out of control. SOHO was never designed to not point at the sun. And so when it started tumbling, the arrays went off the sun, it lost power, we lost the ability to communicate with it, and it literally froze. We then spent the next 4 months working to recover the vehicle. Using radar in Arecibo, we were able to determine where the spacecraft was located, how it was oriented, and we also figured out that it was actually tumbling in a way that the arrays were kind of paddle wheeling, and the arrays were edge on to the sun. Like, wow, okay, edge on, you're never going to get power back. Arecibo was also able to allow us to predict how the spacecraft motion would normally progress just as it went about its orbit. And we were extremely fortunate that it was moving in a way that eventually more and more of the array surface would be exposed to light and that it would indeed get power into the system. When that happened, we were able to reestablish communication, and then we strategically sent up series of commands to thaw it out from the inside out. We needed to be able to thaw the propulsion system and key sensors so that we could then command it to repoint at the sun. Once we were able to do that, it's like flipping on a switch. All of a sudden, you had all the power you could imagine. We had solid communications, and we were able to fully recover the vehicle. However, that 4 months was really the start of the recovery, because when we froze the spacecraft, they don't really enjoy that. We actually lost the functionality of all the gyros. SOHO was designed to always use gyros for its guidance and control. In fact, it had 3 of them because they wanted to have so much redundancy that it would never fly without them. And when they froze, they all broke. And so we then spent the next 2 years redesigning that spacecraft to operate gyrolessly. We rewrote the guidance and control laws, tested it on the ground, had to upload it into the vehicle kind of real time, recommissioned the entirety of the spacecraft, and 2 years later, it resumed science operations. Today, SOHO has been operating for more than 25 years, and it's observed more than 2 full solar cycles worth of science data. Long-term, SOHO is probably going to go down as one of the most successful heliophysics missions, and some of its accomplishments are enumerated here. It's discovered more comets than any other platform, but perhaps the other truly notable thing about the mission is it really pioneered and started the discipline of space weather, which is extremely common and useful in the world today. Looking back, what I took away from SOHO as kind of like the crux for me was the team. Right, I was extremely fortunate to have the opportunity to work with some of the best engineers from across Europe, some of the brilliant scientists at NASA Goddard, all the way down to recent grads like myself. And it was that team and how we worked together and how we struggled and recovered the vehicle that I walked away with a firm foundational principle that I've carried forward on teamwork and the value of what a team can accomplish. When I moved over to APL, the first major program I worked on was Messenger. Unlike SOHO, Messenger was not an expensive mission, comparatively, right? It was a discovery class mission, and the whole mission took about $470 million. And yet, all that said, it was the first mission to ever orbit Mercury. It was the first mission to image the entirety of the planet. And Messenger had a number of unique technologies or capabilities that it demonstrated. It used electronically steered phased array antennas for communication. It had a sunshade that literally kept the spacecraft from melting when it's, as close to the sun as 0.3 AU. It also demonstrated solar sailing as a navigation technique during our cruise. And in fact, the cruise itself, which is running in the animation in the upper left, was revolutionary in its own right. Because it was a cost-constrained, mass-constrained mission, we couldn't carry this giant propulsion system and just fire a big engine to capture into orbit at Mercury. So instead, we did a bit of a tour de force of the inner solar system. And so to get to Mercury, we used 1 Earth, 2 Venus, and 3 Mercury flybys, combined with 5 propulsive deep space maneuvers, so that ultimately we could match the spacecraft's velocity at a point that we could capture into Mercury orbit. Messenger was launched in 2004, it achieved orbit in 2007, and then went on to do more than 4 years of orbital operations to round out the science mission. And not only did it achieve all its science objectives, it far exceeded them, like 4 to 8 times more than was originally planned. You can see some of the highlights here of Messenger. I'll point out, again, despite all the technology and all the great accomplishments, what made Messenger special was the team, the talent, the people that came together to make that mission a reality. At this point in my career, I've been working just over 10 years. I've spent a lot of time doing INT, right? I went through Messenger's INT. I was part of New Horizons INT. That's when you build the spacecraft in the clean room. I've been through multiple launches and post-launch operations. I was really kind of itching to get to the front end of a mission lifecycle and stop inheriting somebody else's decisions, but have chances to make my own and to start working on new mission concepts and new mission designs. So I switched over into the system engineering group, and I started working what we call advanced concepts, and that's early mission concepts. And I was fortunate. I had an opportunity to be part of a group that architect an early Europa flyby mission, which has now evolved and actually become the foundation for what we will know as Europa Clipper, which is going to launch soon. And I had opportunities to work on proposals to Venus, to Io, Uranus, other exciting places in the solar system. But I think my favorite was Time. Time is the Titan Mare explorer. In my heart, I'm an explorer, and engineering is the medium that I choose to use. Had I been born a couple hundred years in the past, I would have been in line to get onto those tall ships and go figure out what's on the great horizon beyond. And so in the era we live in, exploration is done through space. And Time kind of embodied that exploration principle. It's kind of romantic. We were looking to not just send a spacecraft, but a boat to sail on an alien sea. And you can kind of close your eyes and imagine you have this vehicle and it's just gently rocking on an alien ocean. You can almost hear the liquid lapping up alongside of the vehicle, and it just embodied that sense of exploration to me. Time was also where I first fell in love with Titan. And so this is a surface map of Titan. Some of the key features, as you can see, the Selk crater here in the center in the Shangri-La Dune Fields in the low latitudes. And up here are the Titan seas in the high northern latitudes, Kraken and Ligeia Mare. To give you a sense of scale, those seas are about the size of the US Great Lakes. And so they're permanent bodies of liquid on Titan and fairly large. One of the key features of Time is that we weren't sending a traditional spacecraft or a traditional lander. We were sending a boat. So to the best of my knowledge, it's the only boat that's really been proposed in NASA's history to go to an alien world. And so to do that, we really had to try to understand the dynamics, right? We weren't going to land. We were going to splash down directly into the seas. We had a direct entry. Titan, thankfully, has this big atmosphere, and so you could do a direct entry to it. And we were going to splash down much in the same ways that the human capsules splashed down the ocean in the 60s and 70s. And so we had to do a lot of research. And so we did a lot of work with scale models, computational fluid dynamics to understand what would happen when we splash down, how deep would we sink, how long would it take for us to float back up, how would we behave as a buoyant vehicle. It turns out that we actually behave a lot like a buoy, right? If you think about a big tsunami buoy that sits there and floats out in the oceans, Time was designed to behave very similarly to that. And I wanted to call out this research because it was critically important to the project. But what I found most interesting is at the time, this research was primarily done by university students. And so it's an example where you can get people in critical research areas at the universities that have an opportunity to contribute significantly to these kinds of missions. Now, when you do a proposal, and anybody that's ever worked on one, and there are some people here that will understand this, you put a little bit of your heart and soul into every single one. You have to kind of commit to the mission, and it's a huge time commitment. My wife used to always call my proposals my mistress because it's almost like you're married to them because you're spending that much time at work rather than at home. And I personally believe one of the hardest things to do in all of NASA is to actually win a competitive mission. To give you a sense of why I say this, competitive missions are awarded after NASA puts out an announcement of opportunity or an AO. Well, those only come out every so often for planetary missions in particular. Discovery class missions, you have opportunities about every other year, but New Frontiers class missions, which are NASA's largest competitive mission, come out about once a decade. And so these opportunities are few and far between. And every time a new opportunity comes out, you probably get, on average, 30 brilliant new mission proposals submitted. And out of those 30, one is the lucky winner that gets to move forward. So having done quite a few proposals, I can now look in my office at work and I have a bookshelf of binders with fancy graphics and all kinds of pros that go nowhere. They collect dust. Unfortunately, Time is one of those binders. It did not proceed forward. And so it's a bit shocking and jarring, right, in your career when you fail, right? You fail to win the proposal. You fail to achieve the objective that your boss gave you, right? You're not bringing in new business. And so every time afterwards, you take a bit of a step back. And so after Time, I kind of took that one personally. I took a step back and I started looking at myself thinking, well, what can I do to kind of improve myself? How can I pivot my career to better enable me to help lead one of these things successfully in the future? And one of the areas that I deliberately wanted to work on was my leadership skills. I'd had technical roles as a leader on projects, but I deliberately now inserted myself into line management. It's a different flavor of leadership because it's not based upon the engineering. It's actually based on people skills, right? And I had to learn that my success was measured by making the people who work for me successful. And so you work through others and you empower others. But that also taught me a lot about collaboration, empowerment, interpersonal skills. And all of these are really hallmarks, I believe, in good leadership. And so I learned a lot by inserting myself into line management. Eventually, I was fortunate that people empowered me to be the group supervisor for the Space Systems Engineering Group at APL. This is a group that produces mission system engineers, spacecraft and payload system engineers, but also provides the core system engineering discipline, requirements in V&V management, fault management, reliability, enterprise and model-based systems engineering, right? If you need a system engineer in space, you're coming to my group. So it also gave us access to all the programs. It gave us access to national security space, civil space, and I was able to build up my network, both inside the lab, but also with a lot of the companies we worked with and the organizations that we interacted with. And so it was a really good kind of growth experience for me overall. One of the other interesting things about working at APL is they don't actually fund their line management full time. They want you to continue to do technical work all the time as well. So I had to find other activities to round out my day. One of the areas that I wanted to deliberately become more engaged with was hardware development and particularly technology development. And so two examples of things I was fortunate to get exposed to are up here. The first is radioisotope power systems. I had a direct assignment as a part-time person at NASA Glenn, where we worked to develop the next generation of essentially nuclear generators that are used to power deep space exploration vehicles. Today, they're actually transitioning into fission systems and looking to power human settlements on the moon or Mars. And that all comes out of that same group. And so, at some point, you just go too far away from the sun, or you need more power than you can get out of solar energy. And RPS systems and fission systems are terribly enabling. The other area that I had the privilege of being involved with was working with groups of people from NASA Ames and NASA Langley on entry, descent, and landing, or EDL technologies. So I worked with a group that developed the ADEPT system, which is a mechanically deployable heat shield. So it could fold out to 5-6 meters bigger to get large payloads down to the surface of Mars, but still fit inside the fairing of a launch vehicle. Project Pterodactyl took a scaled down version of ADEPT and added control surfaces so you could do a guided entry rather than just a ballistic entry. And then I also was on a review board for a product called HEAT. And that was a new woven thermal protection material that was designed to be the TPS for extreme environments such as Venus landers, right? And we needed to come up with a technology that enabled the missions people wanted to go execute. Then in 2016, everything changed. At this point, APL was preparing for an upcoming New Frontiers announcement. So I mentioned New Frontiers is the largest competitive proposal cycle that NASA does. These missions are about $1 billion, excluding launch vehicle and post-launch costs. They're also the largest PI-led mission. So you have one scientist who is the head of the project. The other unique aspect of New Frontiers is it's not an open call. They have a list of destinations that you can propose to. So this last round, they were specifically looking for comet surface sample return, Venus in situ landers, things like that. We'd been working on several concepts that we were planning on to propose for almost a decade, maturing technologies, developing our designs. And then at the last minute, NASA said, hey, we're going to add destinations to that list. We're going to add ocean worlds. And all of a sudden, Titan and Enceladus were possible proposal destinations. My boss comes like, oh my God, we got to repropose the boat, right? I mean, that was cool. Everybody loved it. We got to repropose the boat. Well, unfortunately, the boat was not a possibility. The way that Saturn and Titan evolved in their natural seasons, the high northern latitudes on Titan were no longer directly visible from Earth. And so we couldn't go there and communicate back. So the boat wasn't an option. Nonetheless, we got a group of individuals together, many of us that did work on time in a conference room, and we started brainstorming. And that brainstorming session was really the birth of the concept that would go on and become Dragonfly. And Dragonfly is an MMRTG powered dual quadcopter rotorcraft that takes an in situ science platform down to the surface and then relocates via flight to different points on the surface to achieve our science. A little bit about Titan. Titan is a strange yet uniquely compelling destination in the solar system. One of the fundamental things that we don't know scientifically is we don't really understand how life came to be on Earth in exactly how it evolved from chemistry to biology, right? That transition is a major question we're still trying to answer. And on Earth, there's been so much biology that it's overwritten all of the evidence to figure out what happened and how we went from prebiotic chemistry to the life planet that we know today. There are places in the solar system that give clues to this, right? Enceladus, Europa, terribly exciting destinations, and they will help us understand this. But Titan is unique in that it is the most Earth-like body that we see in the solar system, and we think it may hold the keys to understanding our chemical origins. Now, Titan is the largest moon of Saturn. That said, it fits right in amongst the planets, right? It is a little bit smaller than Mars, yet it is larger than Mercury. It has a thick, dense atmosphere. It has a solid surface. Its bedrock happens to be frozen water ice, and it has a subterranean ocean underneath. So it's really quite at home amongst the planets. Some other key features about Titan. It has 1/7 the gravity that we experience here on Earth, yet its atmospheric density is more than 4 times greater than what we have here on Earth. And when you couple these things together, Titan's actually an ideal location for flight. I promise it's the only formula I have in the presentation because, trying not to do the typical engineering talk. If you look at the power necessary for a rotorcraft to hover, the major inputs into that are its mass, the gravity, the density, and the area, where the area is the area carved out by the rotor. So a helicopter has one big area on top. For us, it's 4. And so if you compare the power to fly on Titan against the power to fly an identical vehicle on Earth, on Titan, it takes about 2.5% of the power it takes to fly on Earth. So it's really ideally suited for heavier than air flight. In fact, as a human, if you were to just go to Titan and had wings and flapped your arms, you would lift off the ground. You would be able to fly. The other key attribute of Titan is that it is cold. It is 94 Kelvin on the surface or minus 180 Celsius. So in terms of Dragonfly, we are looking to live, survive, and operate in a cryogenic environment. And that adds its own complexities in designing a mission. Titan has all the necessary ingredients for life. You have sunlight and photochemistry that takes place in the upper atmosphere. It forms these complex organics that then rain down like manna from heaven to the surface. Titan also has 2 liquids, right? We know that there's water in a subterranean ocean. We believe that there are paths for the water to make it up to the surface through cryovolcanoes or impact melt. And we also know conclusively that it has liquid methane. In fact, Titan has a methane cycle, which is one of the ways that it's very Earth-like. Methane rains down, it collects into streams and rivers, flows into lakes, large bodies of permanent liquid, and then evaporates back. We have photo evidence of clouds on Titan and winds on Titan. And so if you were to look at it just graphically in pictures, it would look strangely similar to Earth. You would see mountains and lakes and clouds and rain. And so in many ways, because you have all the necessary ingredients on Titan, what truly makes it stand out is it is the only place we're aware of where you can study this prebiotic chemistry on a planetary scale, right? The full scale of the moon, where you actually have that level of Earth-like processes taking place. We're also extremely fortunate to have had the Cassini-Huygens mission go before us, right? Huygens was an ESA-provided probe that already landed on Titan. And from them, we have good measurements of the atmosphere, and we understand what it's composed of, what the winds are like, and so forth. And that helps us design our mission. Cassini also performed over 100 close flybys of Titan. And so they have high resolution imaging. They've shown us that there are these geological processes. They have measured for us what some of the constituents are. And so because of Cassini, we know where to go to look for the questions or for the answers to the questions that we have. Now the challenge became getting there, getting a large enough science platform down to the surface and being able to make more than a point measurement, but be able to make measurements from multiple locations. I mean, if you were another species coming to explore Earth and you landed a probe in the middle of New York, and then you landed a probe in the middle of Africa, you're going to get very different impressions on what the Earth is like. Titan's no different. We need more than one point measurement. We need to be able to explore a broader range of the surface. And when you couple that with its natural environment and the enablers, heavier than air flight became the obvious way to get around, right? It was more efficient than a rover and driving, and you can go farther and hit more types of terrain. So Dragonfly is composed of 4 main mission phases, right? They're the fairly traditional ones. You have launch, and then that is followed by cruise. Cruise is the process by which we get from Earth to Titan. Our cruise will take about 6.5 years, and that's the fast version. When we originally proposed the mission, we were looking at a cruise period that was closer to a decade. NASA, thankfully, is going to give us a larger launch vehicle, and so that's going to help us get there faster. We have EDL, or entry, descent, and landing. We are doing a direct entry. Again, that Titan thick atmosphere helps a lot. It's like firing a bullet into a pillow, right? So I don't need to do an orbit insertion at Saturn. I don't need to do any burns at Titan. I just have to, target the moon properly. And then that thick atmosphere combined with an aeroshell and a series of parachutes allows us to take about 2 hours to descend from the highest point of the atmosphere down to about 1.5 kilometers off the surface. At that point, the lander will drop off from the back shell and use the onboard flight system in order to land down on the surface. Most of our science is done on the surface while we're stable. And all of our communication back to Earth takes place on the surface while we are stable. I will preface that we do some aerial imaging and we do some atmospheric profiles during flight, but the preponderance of the science is actually surface measurements. A little bit about our flight system, back up to point. So the spacecraft, which comes off the launch vehicle, contains a cruise stage on the back end, and that houses the propulsion system, thermal, guidance and control, and everything we need to make it out to Titan. The entry vehicle is what we refer to as the EDL assembly, with the lander contained inside. The EDL assembly has the heat shield and then the parachutes and all the equipment that enable the descent. And then, of course, the lander itself contains all of our science instruments, all the equipment necessary to communicate back to Earth, all of the flight processing, and all of the capabilities that make the vehicle itself fly at Titan. There are a few key enablers for Dragonfly as a mission. We are fundamentally enabled through the use of an MMRTG. This is the same nuclear battery or nuclear generator that people use on Mars. It's the exact same model that has flown both as part of the Curiosity and Perseverance rovers. And on Dragonfly, not only is it our power source, it's our heat source. I talked about how the surface of Titan is extremely cold. We get about 2,000 watts of thermal waste heat, if you will, that we trap inside the lander by keeping the whole body encased in foam. We trap all that heat, and that's what keeps our electronics and our equipment warm. And then we use the energy to power the vehicle, although I have to point out the RTG itself doesn't produce enough instantaneous power to actually facilitate flight. So instead, we do all of our operational activities off a very large lithium-ion battery, and then we use the RTG to recharge the battery during periods of hibernation during the Titan night. Unlike Mars, we do not have an armada of spacecraft that we can use as communication relays. And so Titan's far, it's about 10 AU from Earth, and we have to do direct to Earth communication. So we use our high gain antenna that you see deployed here, and we communicate directly from the surface back to Earth. Additionally, I already mentioned this, but we do the majority of our science on the surface with some aerial measurements. To give you a sense of scale of how big Dragonfly is, it's about 5 feet tall, 12 feet from nose to tail, and about another 12 feet tip to tip across the rotors. So it's not a drone, it's a drone, right? And to give you a real world sense, think Mini Cooper, right? We're essentially sending something the size of a Mini Cooper to go fly on Titan. And you can see here in the insert a picture of our PI, Dr. Elizabeth Turtle, holding a full-scale rotor. And so that's a good kind of tangible way to get a sense of how big this vehicle is. I have to talk about the instruments. So Dragonfly contains 4 instruments and a sampling system. So our instruments are a mass spectrometer, which does molecular level analysis of material from the surface, where the sampling system has drills on either side, and then we pneumatically move material from the drills into the sampling system. Titan gave us an atmosphere. What's easier than an old-fashioned shop vac? We have a geophysics and meteorology package, and so we have sensors scattered throughout the vehicle. It's going to measure temperature, pressure. We have geophones for seismology, methane content. Think of it as a traveling weather station. We have a camera suite because every NASA mission has cameras. We actually have 8 of them. We have forward and downward cameras. We have micro imagers that will do high resolution imaging at the drill sites. And then we have panoramic cameras where we can use the gimbal on the high gain antenna to take panorama views of Titan around us. And lastly, we have a gamma ray neutron spectrometer, and this gives us bulk composition. So when we land somewhere on the surface, are we landing on a pile of organics? Are we landing on ice? What is the surface that we've landed on? And so the gamma ray allows us to do bulk composition. We've already picked our landing target, and we've done this for 2 reasons. The first and foremost is science. If you remember when I had that full view of Titan, in the center was the Shangri-La Dune Fields and the Selk Crater. We are targeting a landing area just south of Selk Crater. And we did that scientifically because it gives us access to dunes and inner dunes, as well as the impact ejecta of the crater itself, where we hope to find water melt. And so we get access to different kinds of materials, different kinds of geologic settings, and that's what we need to satisfy the science requirements. Additionally, we're fortunate that this is some of the highest resolution imaged portions of the surface from Cassini. And so we know that there are dune fields, and you can see, it's a little hard to tell in this image, but you can see these broad lateral dunes, and they're analogous to the Namib dunes here on Earth in Africa. So you have these dunes with wide, multi-kilometer span inner dune areas that are basically flat and hazard-free. And so when you're landing somewhere for the first time, that's good, right? No hazards, no rocks, no boulders. And so technically, it was an ideal landing site as well. Once we make it down to the surface of Titan, we also have a bit of a unique exploration strategy. So once we check out the vehicle, we're in a spot that we've already landed. So we know this is safe. From there, we're going to do scout flights and go explore different potential new destinations to fly off to, but come back to where we started because we know we can safely land there. Then we'll bring back to the ground the data and the images of those potential sites so the scientists and the engineers can comb through that data and say, scientifically, I want to go there. Technically, yep, that's safe, and then pick the next place to go. From there, we execute what we call leapfrog strategy. We'll start in our original site. We will go fly over where we've already designated as our new or second site, continue, then go down and scout out the second new potential site, but come back and land in our target destination. And again, once we're here, we'll bring this data back down to the ground so we can decide, is that indeed where we want to go next? So 2 steps forward, 1 step back. And it's designed to be a conservative, low-risk approach towards exploring a place where we really don't have enough a priori information to really get around otherwise. And so it puts ground control in the loop in the decision-making on how we navigate the surface. As we traverse, our general goal is to go from that landing ellipse towards the crater to get into its ejecta region. And so we'll start in the dunes, and then we'll work our way to the inner dunes up towards the ejecta blanket as we go from somewhere up here up in this general direction. And the coloring here shows you that there's different types of materials and different types of terrain. And again, that's what is compelling from a scientific perspective. I should note that the scale on this plot is exaggerated in one axis. It is meters in height and kilometers wide. So from the axis over here up to about where the star is, that's a little more than 100 kilometers. But the height here is only about 200 meters, just to help you understand the graphic a bit better. Right now, we're planning a primary science mission that's just over 3 years. During that time, we are hoping to traverse net range more than 180 kilometers. For perspective, that is farther than all of the rovers of Mars have gone combined. So we really will get to explore a fairly extensive portion of the Titan surface. And we anticipate having 25 to 40 unique sites that we will go visit from a scientific perspective. So I've talked a lot about the design. The design hasn't changed that much from what we proposed and were awarded back in 2019. We are working now to convert the concept to a real design. So we went from pretty PowerPoint to now having real drawings and specifications. We're coming up on our preliminary design review this fall, but I did want to highlight some of the great work that's been going on during this time. What you see here, we refer to as an ITP. It's an integrated test platform. It's a half-scale drone that we are using to mature our surface flight development. So our guidance and control algorithms, it has 8 independent rotor assemblies, so motor and rotor combinations. It has many of the same sensors we will use to fly and navigate on Titan. LiDAR, IMU, navigational cameras. It is running flight code that we've written at APL, running on a flight-like commercial processor. And it integrates all of this as we develop our guidance and control and our autonomous flight capabilities. So recently, we actually took the ITP out to the Imperial Dunes in California. We've also taken it out to Yuma, and we are conducting testing in an environment that is similar to the terrain that we expect to see at Titan. We test early in the morning and late at night to get different lighting conditions. I'll point out, although you saw there was a pilot there, they're not flying this vehicle. They're there for safety. They're there to make sure it lands safely because it's fairly expensive. We don't want it to crash, and to make sure nobody gets hurt. But the vehicle takes off and flies autonomously. It does have GPS, again, not for navigation anymore, but now to have a comparison point against the onboard navigation. And so we've been able to establish that our onboard optical navigation lines up pretty close with the GPS and exceeds the precision we're going to need on Titan. And so we've been able to demonstrate a lot of our mobility capabilities in advance of PDR. We're going to continue to mature this and then eventually incorporate autonomous landing. And that's kind of the last major hurdle, and then scale everything up to full size. So Dragonfly is also a big project. It takes a lot of talent and a lot of different types of talent to make this mission successful. We've drawn from organizations, universities, national labs, NASA centers from across the country, throughout Europe and Asia. And you can see some of the key partner organizations listed here. However, you don't have to go that far to get involved with Dragonfly. And I wanted to point out that one of the mission co-Is, Dr. Sarah Horst, is right here at Johns Hopkins. And she has her lab in the Earth and Planetary Science area. And they are doing fundamental research on planetary chemistry. And her research will help lay the foundation for us being able to understand and assess the habitability of Titan when we get there. And not only is her research supporting projects like Dragonfly, really it's applicable to any of the planetary bodies in the solar system with an atmosphere, with chemistry. So she also has a group of students that are producing a student-built instrument that's going to fly on another NASA mission, Da Vinci, and will actually make it to the surface of Venus. And so right here on campus, you can go and do fundamental research that will influence planetary missions. I just thought that was kind of cool and like the direct tie-in. Lastly, maybe you're seeing a theme. Much like several of the other great projects I've been privileged to work on, SOHO and Messenger, Dragonfly ultimately is going to come down to the team. The large picture here is a team photo we took in 2019, right after we were selected. The insert was from a team meeting we had last year, and so you get a blend of people outside and people on Zoom because of COVID. We have an incredibly talented team. That said, COVID has been challenging, right? Building a team in the middle of COVID, going from a proposal with maybe a couple dozen to a team that's now over 300 is challenging. You just don't get the same interactions across a computer screen. Yet they're extremely talented and they are the heart and soul behind everything I've shared with you today. And it's them and the teamwork and all of us coming together that's going to make this mission successful. So as I was pulling together the presentation and anticipating talking with an audience of students, I thought it could be useful to look back. And for me, looking back, there are things today I certainly wish I knew then. So I thought I'd take a brief moment and share some of those. One, I've hit this point multiple times. People really are the most important part of what I view as my job, right? They are the enablers. It's not the machines. It's not the technologies. It's the people. It's the people that make up the teams. It's the people you lead. And when you move on from project to project, what you will remember are the relationships, the colleagues, the friends. It's the people that will touch you, that you will impact, that is the greatest leave behind. Seek mentors, formal, informal, always. I have a mentor today. I had several mentors in the past. You are never too old to learn from somebody new and to learn new things from other people. Ask questions often. In my view, the only bad question is the one that nobody asks. And the reality is, if you're wondering it, someone else is probably asking in their head the same thing. Lead by example. Again, I've been fortunate to have been empowered to be a leader at times in my career. You have to earn respect. You cannot get respect because you have a title or because someone bestows it upon you. That just doesn't work. You have to earn respect for the people working for you. And that comes through your actions and how you treat people. And so to me, one of the big things I always said is I don't ask anything of others that I'm not willing to do myself. And you can go watch a simple restaurant and see good leaders versus bad leaders. You're in a restaurant and the owner's standing around just watching everybody, you know, there's a line waiting by the door and tables that need to be bussed. Not a good leader. The owner that rolls his sleeves up and takes the dirty dishes back into the kitchen and helps seat people just because there's a lot going on and they need the help, that's a good leader, right? Because they're willing to jump in and do whatever it takes to be successful. And then the staff see them doing that and they respect it and they will work harder for that individual. Be humble. And what I mean by that is invariably, there's someone smarter than you. I promise there's someone smarter than me sitting in this room. There's someone more talented than you. It's a big world. There are a lot of people, and we want to embrace diversity of thought and experience. All of that diversity, when you add it into that team mix, makes everybody stronger. And so embrace that and look to incorporate that. Spend more time listening than talking. It's a little ironic since I'm up here talking for 30 minutes, but in general, listen more. I think that speaks volumes. And lastly, particularly for the younger people in the audience, your career is not going to be a straight line. It's going to zigzag. New opportunities are going to present themselves. In many ways, your career is what happens while you're planning what you want to do. But that's okay. My experience has been that it tends to always work out, and often it does so in new and exciting ways. So I'm going to end with a final animation of Dragonfly and its arrival at Titan. It was kind of refreshing for me looking back, and I talk about how your career kind of takes a crooked path. My career kind of all led me to this moment, right? I had opportunities to work on large, complex missions. I had opportunities where I was exposed to executing low-cost planetary missions. I've had various leadership opportunities. I've been exposed to nuclear power sources, to EDL technologies, to a wealth of brilliant planetary scientists and incredible engineers, and been able to take all of that and kind of leverage it into the job I have today on Dragonfly. And you can see it all comes into play. We're going to need a team. We're going to need certain new capabilities in order to go do this incredible mission. And if you talked to me 10 years ago, I never would have envisioned this, never expected it. But here we are today on the precipice of flying on an alien world. And that's just incredibly exciting and incredibly cool. Looking back at last century, you'd often hear people talk about planes, trains, and automobiles. Well, for me in my career this century, it's really been all about spacecraft, boats, and rotorcraft. Ironically, all of which are useful in planetary exploration. So with that, I will simply say thank you, and I'm happy to take any questions.
Thank you very much, Ken. I think we have some time for questions, and I'll try to run around with the microphone if you have a question. Questions from the audience?
What did the boat project lose out to?
What did the boat project lose out to? It lost out to InSight, which was a Mars lander. It was a stationary lander on Mars that was doing tectonic observations. So it was global seismology on Mars.
I had a question about how you deal with the fact that it's an exploratory mission. So you're obviously looking to learn things. So you don't know everything about the environment going in. Obviously you have the probes like Cassini, but in general, how do you build that into your design and your mission design?
Carefully. We try to make the mission robust. So we've tried to bound the wind profile we might see. We're trying to bound the surface that we might experience. Is it really hard? Is it really soft? We have to think about whether or not we're going to sink into the sand or bounce off the ice. And so you try to come up with you guesstimate on all the different environments and you bound your performance. There are some things that we just say, it's out of scope. And if we experience that, we have a bad day, right? That is part of exploration in space. It doesn't always work. We all want it to, but we all, know that we push the envelope a little bit. So we try to bound it in engineering principles and then make the system robust to that. So you have a broad range of capabilities you can apply.
Hello. Okay. I was just curious about how you incorporate like the end of the design life into the design process. Like, does it influence any materials that you pick, or like, just how does that factor into design?
So we actually design for end of life. The MMRTG is a good example, right? So its source is plutonium inside of it, plutonium-238 that decays. And so our power that the RTG puts out and the heat that it puts out degrades over time. When we launch, it will put out about 120 watts. When we arrive at Titan, that's already down to about 90. When we end the prime science mission, we're already close to 80. So we've designed the system can survive and exist down to a minimum output power close to 60, right? Something in that area. So again, we have some margin built into that so we can have an extended mission. Same thing with the thermal output. From the materials, you actually have to think about how the materials are going to behave. So the rotors are a good example. We have to consider that they're in a cryogenic environment. So they're cold, and that's going to make them brittle. And we have to understand fatigue and how the material properties are going to erode over time. And so ideally, if I was flying this craft on Earth, those rotors would be composite materials, right? Lightweight, much easier to fly. On Titan, I can't do that because I don't have composite materials that will survive in a cryogenic environment for that long. They'll become too brittle and eventually would likely break. Also, if there's dust or particles, they could, damage the leading edge, things like that. So we do have to look at all the materials. We do material testing. We're going to do lots of analysis and try to get as much of that into the design process up front. There's a lot of work that goes on behind the scenes, mechanically, thermally, and so forth, to assess the materials and understand how all the properties are going to behave at the end of the mission. And then we add margin, and that becomes our design point going forward.
Hi, this is more of a technical question, but you said Titan had a thick atmosphere, and so that raises like questions in like turbulence and wind strength and storms. So I was wondering, like, are there storms and like strong winds on Titan? How does Dragonfly deal with that stuff?
It's a great question. Thankfully, no. So one of the things we have from Cassini is we have a pretty detailed atmospheric profile. We're also fortunate that our mission architect, Dr. Ralph Lorenz, is probably the leading Titan expert in all the world. So they have a profile of the Titan atmosphere. We operate in the lowest portion of the atmosphere, right? We really live between ground level and about a kilometer or two over the surface. Anything below, say, roughly 10 kilometers, it's pretty benign, right? Their typical wind is 0. A wind gust is on the order of 4 meters per second. So it's not too bad. Now, there are headwinds, just the motion of the vehicle through air will create headwinds and tailwinds and things like that. But it's not like on Earth, right? We're not expecting big, tens of meters per second gusts to come along and push the vehicle around. Storms, it's possible. Again, benefit of Cassini is they did almost an entire Saturn season. And the time of Saturn's year that we are there is not the storm season. Additionally, the portion of Titan that we're on is not, common for those kinds of events to occur. Is it possible? Yes. However, we think it's extremely unlikely that we would experience rain, heavy windstorms, or anything like that. If we live long enough and the seasons change, perhaps. But again, we've tried to make the vehicle robust, but there are some conditions that if they just naturally occur, we have a bad day, right? You can't do everything in a limited cost bucket, right? If more money, we can do more. But so we try to strike that balance.
Hi, considering Titan has a different gravity and different atmosphere, how do you, when testing Dragonfly now on Earth, how do you mimic Titan's condition on Earth?
Good question. We actually cannot fly the full-scale vehicle on Earth. So we do a lot of modeling, right? Because in modeling, it's easy to go in and edit the atmospheric parameters. You can scale for Froude and Reynolds and viscosity and all of that. We test piecewise in a series of chambers. We take full-scale rotors and the motors that are operating them. We call that the drivetrain, really from the power source all the way out to the rotor. And we're using a facility at NASA Langley called the Transonic Dynamics Tunnel, or the TDT. And they have a heavy gas capability. And so in that wind tunnel, we can replicate some of the Titan conditions. And so we use testing in facilities like that to validate our models. And then we use the models to facilitate the design. Similarly, we are building we've built 2 thermal chambers at APL. One is 5 foot by 5 foot by 5 foot, and it is, we call it the TPEC chamber. It is a Titan pressure environment chamber. It can get as cold as minus 170 C and up to about 1.5 bars. So it's pretty closely replicating the Titan atmosphere. And then we're in the process of installing what we've called the Titan chamber, which is a large 15 by 15 mailbox shaped chamber that can get down to Titan temperatures, but only up to 1 atmosphere. Because most facilities have really cold vacuum chambers. And so we didn't find a chamber that was cold and atmosphere, so we built our own. And so we're going to use those to heavily test the equipment.
Thank you for a fascinating talk. Given the name, I can't resist asking about lightweight materials and lattice-like materials that you might be using. And I'll couple that with the second question, and that is, with the emergence of new technologies and new materials all the time, how do you lock in your design parameters? How do you decide when and where to do that?
In terms of materials, I don't know that. So the cryogenic environment makes it challenging, right? And so we're probably heavier than we would like to be, right? As all spacecraft are, right? You'd like to make them as light as possible. I wish I could do more composites. They don't work great in cold. We are doing a lot of magnesium boxes and titanium rather than aluminum because they work well in our environment and they save mass. The foam that we use for insulation is extremely lightweight. It's about 2 to 3 inches thick. It's Rojo cell foam. It is a great thermal insulator and it's extremely light. So that helps. Our antenna is a radio line slot array. So it's a flat disc and it's basically 2 metal plates with foam in between that conducts the wiring. And so it's a very lightweight antenna as opposed to a parabolic dish that wouldn't swing around very easily. So we've tried to save mass everywhere we can. But there are just some places where, like the rotors, I can't go composite, I'm using metal. In terms of locking down the design parameters, it's an evolutionary process. So you're forced by the government with certain milestones, right? So when I had to submit the proposal, I needed a concept. We gave them a concept, but it's ill-defined, right? There's a lot of work to do. I don't ever call that a design. We are working right now to convert that concept into a design. And so we've been working on that for the better part of the last 2.5 years. So what that is doing is making some of these choices, right? And so we're making material choices, we are choosing designs, and we are converting it into specifications and drawings again. After our preliminary design review, we'll get feedback. We'll find things that an independent review board comes in and says, love that, hate that, right? And we'll get a list of feedback and things to go refine, correct, look to optimize, right? They come in these joyous action items that we all have to work off. Then we have about another year or so before our critical design review, and we'll work through all of those actions so that when you get to the critical design review, you're saying, this is my design. This is my line in the sand. And that is the gate after which you go and cut metal and you start fabrication. Now, a system like this, we actually have to treat it more like an aircraft and less like a spacecraft. And anybody who's designed an aircraft knows that you're optimizing to the very end, right? So we are going to be looking to optimize our mass to the very end. We're going to be looking to lightweight the vehicle, to balance it, to get as much power out of it as we can. So there's going to be a low level of continuous optimization throughout the development cycle while we can. Because once it leaves Earth, you can't touch it again. So, but the major decisions happen early in the design process.
I know we have quite a number of more questions, so we'll take a couple more, and then we'll have an opportunity to just talk informally.
Sure.
But let's just take a couple more.
Thank you so much for your talk. It's incredible work. So I guess kind of a coupled question. Will the Dragonfly be able to be remotely controlled in like situations like major fault recovery? And what are just some general kind of major fault recovery strategies you guys have been thinking through, some implementations that you might already be having for things like that?
It cannot be remote controlled. Our round trip light time, or our one-way light time, so to get a signal from Earth to Titan is roughly an hour and a half. So to go from Earth to Titan and back, 3 hours. It's not remote controlled. It has to rely on an onboard autonomous system. In terms of faults, I'm assuming you're talking mostly while we're in surface flight. Couple things. Every component that's necessary for surface flight, we've made redundant. So the first tier is if something fails, you switch to the backup, right? And we can switch, for example, we can switch to the backup computer in milliseconds while we're flying, right? So that happens very quickly. We are designed that we can fly without one working rotor. So I have redundancy built into the design of the craft, so I can lose one rotor or one motor and continue to fly. We have redundancy in our battery cells, in our harnessing. So we've tried to make the system robust through redundancy. If there is any problem that takes place in flight, our onboard autonomy system detects that, right? It monitors the telemetry and the housekeeping for all of these components, and it will do the switch over and say, okay, I'm going to maintain my ability to fly, but we're not just going to keep going along our merry path. At that point, we raise a flag and say, something's wrong, right? And it's got several tiers of response for getting down on the ground. The first thing it's going to do is say, am I closer to where I started, a known safe spot, or am I closer to where I was targeting, a new safe spot? And it's going to say, where am I closer to? I'm going to go there, right? So that's first response, is to go to the closest safe landing spot. Hopefully, its performance is such that it can get there, and then it'll abandon the scouting and just target getting down on the surface. If the problem is bad enough that we don't think, the vehicle doesn't think it can get to its first target spot, it will start scouting directly beneath it, looking for a new safe spot. A safe landing spot for us is something with less than 10 degrees slope and no quarter-meter rock or larger hazards in a 8-meter diameter landing circle. And so it will scout around because it has the cameras and all the onboard systems. And effectively what you're doing then is invoking the same process you do on day 0 when we arrive, right? It's looking for a safe landing spot. If you're having a really bad point in time, it may just be head between your knees, get down on the ground and do the best you can. And at that point, it gets down on the ground, it waves the white flag, it calls home and says, help me, help me. And then ground people get involved and we take it from there. So it's a tiered response with a lot of onboard autonomy.
Okay, we'll take one more question. I have one over here. No? Okay, take one over there.
Yeah, so this gets at sort of what, failure, learning from failure, and redundancy in systems, but maybe more generally. Throughout your career, like, have you generalized any best practices or tips and tricks for those of us who are starting our careers to mitigate, plan for, and sort of plan for failure, basically? And we learn a lot from it, but a million miles from home, something can't fail. Right. So throughout your projects, do you have any like best practices that you've sort of developed to plan for that kind of thing?
It's a good question. There are a lot of lessons learned broadly across the industry. So step 1, step outside yourself. Step outside of your organization and talk to other people that have done similar things, because the culture I have at APL is a little different than that at Goddard or that at JPL or Boeing or Lockheed, and they're going to have different lessons learned. They're valuable. So one of the first things we did is we reached out to our peers and said, hey, we're doing a lander. What lessons learned do you have for us? And fold that in. So step out of yourself. Obviously, you do your best to try to forecast all the things that could go wrong, right? There's whole disciplines, reliability analyses, probabilistic risk assessments, fault tree analyses, FMEAs, all of that feeds into what could go wrong, fishbone diagrams, what could go wrong, what do you do if those things go wrong? Those are critical disciplines. They're often underscoped and they're really important. Understanding, you'll never catch them all. You cannot possibly conceive of everything that will go wrong. So you try to make your systems redundant, you try to make them robust. You are constrained by mass or money or other resources. So it's a bit of a balance game. And that's where lessons learned kind of come in to help you. This is probably more likely than this. And so it's a bit of an art form. It's hard to say an exact roadmap other than, building upon the community that's come in front of you is extremely beneficial.
Thank you so much. And let's thank our speaker again. Terrific presentation, and thank you for taking all the questions. I know there are more.
It's my pleasure. Thank you.
I do want to thank again Gordon Croft and the Croft family and Linda and the Bilig family for making this lecture possible. It's great to be back in person. I invite you all to stick around, to talk to Ken, to talk to each other, to network. And when you leave, there is a souvenir of the lecture for you all to pick up. So thank you again.